Hi, I'm Abhinandan Padhi, and this is a short video about my final year project. The title of the project is Deep Learning for Detection and Segmentation of Brain Lesions from CT Scans. Brain lesions are lesions of abnormal brain tissue, and in this FYP we focus on intracranial hemorrhages specifically. ICH refers to the bleeding inside the skull and is caused by head injuries. In this FYP, we conducted research to determine methods to automatically detect and segment ICH in the head CT scans. Objectives were to achieve high segmentation accuracy in terms of dice score and to address the lack of publicly available ground truth segmentation data. The main contributions were that we developed a novel two-step technique for ICH segmentation called Faster RCNN plus EM. It is a combination of Faster RCNN object detection and segmentation using the EM algorithm. It is novel as existing object detection data is leveraged in order to improve segmentation, and also the input to EM is smaller than the whole image, making it more efficient. Datasets used for this FYP were the CQ500, Brain Hemorrhage Extended or BHX, and Radiological Society of North America or RSNA intracranial hemorrhage datasets. The datasets above did not have ground truth segmentation masks publicly available, so we manually annotated 250 slices from RSNA and CQ500 for training and evaluation. Faster RCNN is the object detection architecture we used, and it has three subnetworks, namely the feature network, region proposal network, and detection network. The EM algorithm is based on the idea of the Gaussian mixture model, which means that there are three types of brain tissue based on pixel intensities: normal brain matter, abnormal ICH tissue, and skull tissue. For each of these tissue types, the pixels could be described by a normal or Gaussian distribution. A mix of these distributions is called a Gaussian mixture model. And the expectation maximization or EM algorithm, essentially what it does is it starts with random initialization of the GMM's various distribution parameters, the means and the variance values, and then the parameters are improved iteratively by alternating between the expectation and maximization. Expectation means that for every data point, the probabilities of it belonging to each of the distributions are computed, and maximization means that parameters for each distribution are updated based on the points in the cluster. So here are the 5 types of hemorrhage. And this is the main pipeline. So in the pipeline, we have first the input CT image in the typical medical format, which is the DICOM format, which is converted to a two-dimensional array. We apply contrast adjustment using windowing, and we remove the skull and calcification pixels to improve accuracy. This processed image is input to the Faster RCNN model, which outputs bounding boxes. The bounding boxes output by Faster RCNN are passed to the EM algorithm, which extracts the ICH lesion and then segments it, and this produces a binary output mask which is combined with the original image. Thus, for comparison, we also have the UNet architecture for semantic segmentation. Essentially, it is a fully convolutional network with an encoder and decoder. The encoder learns key features in the image but loses location information, whereas the decoder aims to recover the lost feature location information. Here we see the hyperparameters we used for ICH detection using Faster RCNN, and here we can see the results that we obtained. We prioritized precision in this FYP for the Faster RCNN model, and here we can see the precision per ICH class. Clearly, IPH has the highest precision. However, some classes such as SAH and SDH performed worse, which is important as we shall see later on. And for ICH segmentation, we use the EM algorithm in 3 variants. We have first full-size CT images, then we have ground truth boxes, and then bounding boxes output by Faster RCNN. So here, if you use the full-size CT images, we can see why it is not such a good idea. The image in the middle, image 3, shows the EM output using the whole image, which is clearly not as accurate as it should be, as is shown in the ground truth segmentation mask. Even if we remove the skull pixels in order to account for this, we still do not achieve a highly accurate, accurate output. Thus, we resorted to using ground truth bounding boxes. The bounding boxes shown on the left in image 1, if we take the pixels within those and we apply EM algorithm on that, then we can achieve a significantly more accurate result. Thus, we used this variant of the EM algorithm and with these hyperparameters. So when we're using the ground truth boxes, this is the performance achieved. Dice score is the main is the priority over here, and we can see that the intraventricular hemorrhage has the highest dice score. However, again, subdural hemorrhage and epidural hemorrhage have lower performance. Thus, because of Faster RCNN and EM both do not perform as well on subdural hemorrhages, we can see that the performance is severely degraded for those classes, whereas the other classes like IVH and IPH have significantly better performance. So why is that? The weakness of the model is in faster RCNN. The faster RCNN may output false negatives, false positives, which are anomalous boxes for some CT slices. Therefore, we see that EM produces incorrect segmentation output. And now, if you were to, we could see that the model could be more accurate if there was more data. Thus, to roughly measure how the model would perform with more training data, we could ignore the anomalous predictions of the false positives from faster RCNN, and this increases the dice score 58% overall from the previous value of 48%. This is a comparison with the UNet that we had mentioned earlier on, and we can see that UNet still does not perform as well as the EM algorithm plus as well as the faster RCNN and EM algorithm combined. And this is when this is a comparison with the existing methods, such as encoder decoder CNN, which is an EDNet, as well as patch FCN and attention based units. So clearly you can see that there's actually big disparity between our models and the past methods. This is because of the dataset size. Methods such as EDNet have significantly larger dataset size, whereas we had a very small dataset size just for training the model, the faster RCNN model, as well as for evaluating and for training a UNet and EM algorithms. So this is this suggests that relative to most deep, fully supervised models, our proposed model actually performs quite well with such limited data. With ground truth bounding boxes, EM's dice score was roughly 72%, which is on par with past techniques such as EDNet. However, because EM requires accurate bounding boxes to be extracted during object detection to achieve dice score, we can say that the overall segmentation performance is bottlenecked by faster RCNN. While performance is not ideal, I think it still works well on good bounding boxes, and therefore the proposed two-step pipeline is still viable.